Hey everyone, my name is Max Leamy, and today I'll be presenting the Circuits Lab. As an introduction, the purpose of this lab was to create circuits with resistors in series and parallel to measure the behavior of current and measure current using a multimeter. We also examined and plotted the behavior of capacitors as they charge and discharge. For the results of the experiment, the formulas for the loop rule, node rule, and equivalent resistance can be used to accurately predict current behavior in a circuit. The capacitor charge can also be modeled by plotting the natural log of delta V divided by V underscore zero versus time. For the 200 millifarad capacitor and the 30 ohm light bulb, we calculated an RC time constant of 6.0 seconds. For the physics concepts in the experiment, Kirchhoff's node rule, the loop rule for circuits, Ohm's law, and the definition of steady state were used. Kirchhoff's nodes rule and the loop rule were used to calculate the current going into and out of each node in each circuit, and to calculate the change in voltage or potential caused by circuit elements. Ohm's law was used to find the relationship between voltage, current, and resistant measurements. Finally, the definition of steady state, where the potential is not changing over time, was used to find the time it took to charge and discharge the capacitors. For the first part of the experiment, the system is the circuit and its elements. The surroundings are everything outside of the circuit. The assumptions were that Y resistance is equal to 0 and ammeter resistance is equal to 0. We used the node rule for resistors in series to calculate the current going through a 100 ohm resistor in series with a 47 ohm resistor due to two 1.5 volt batteries. Resistors in series add the resistance values, so we were able to combine the two resistance into one equivalence resistance Req and calculate the current using Ohm's law, 3 volts divided by 147 ohms. We also observed the same current of 0.02 amps using the ammeter, and reversing the ammeter negated the current value. For the results of part 1 of the experiment, we used a voltmeter to measure the voltage change for each circuit element using several points on the circuit. The total change around the circuit loop is equal to 0, proving the loop rule for circuits true. The simulation assumed there is no resistance through the voltmeter. The graph I drew shows the potential difference across all the points measured in the circuit. When removing the 100 ohm resistor from the circuit, the current increased from 0.02 amps to 0.06 amps because we decreased the resistance by 2/3 of its original value. We can calculate the resistance of the resistors, the wires, and the ammeter using Ohm's law, taking the voltage change from the graph divided by the current for the first part of the lab. My results are shown below under 12. For part 2 of the experiment, the system is the circuit and its elements. The surroundings are everything outside of the circuit. The assumptions are again that Y resistance is equal to 0 and ammeter resistance is equal to 0. I constructed a circuit with a 9 volt battery in series with either a 10 ohm bulb or a 20 ohm bulb and a 200 millifarad capacitor. I placed the uncharged capacitor in series with both of the bulbs individually and the power source and observed the bulb getting bright, then dimming as the capacitor charges. I then removed the battery and reconnected the bulb and capacitor in a loop to discharge the capacitor. The bulb again got bright and then dimmed. I measured the time it took for the capacitor to charge with the 10 ohm bulb and the 20 ohm bulb built. Um, with the 10 ohm bulb, it took about 15 seconds to charge and discharge, and with the 20 ohm bulb, it took about 30 seconds to charge and discharge. Finally, I measured the change in voltage of the charged capacitor for 20 seconds after it was connected to a 30 ohm light bulb and allowed to discharge. The results for the voltage change caused by the capacitor at 20 different time points are shown below. I plotted the natural log of the voltage change due to the capacitor divided by the voltage at time equals 0 versus time to observe a linear relationship with the equation y is equal to negative 0.1667x plus 0.0126. The slope of this equation is equal to negative 1 over RC. I calculated the time constant RC to be equal to 6 seconds using the equation. For the first what does it mean question, if we were doing this lab in real life and used an actual ammeter instead of an ideal simulated ammeter, the actual ammeter would have a resistance greater than 0, therefore decreasing the current going through the circuit. If we were doing this lab in real life and used a real battery to charge a real capacitor with no resistor in the circuit, the time constant RC would be equal to 0, so the capacitor would charge instantaneously. This result would not happen in real life, as real life wires have some resistance that determines the current moving through them, and the time constant RC would not be equal to 0. All right, thank you, everyone.